The worst-case scenario for 3I Atlas seems absurd, until you stop assuming it must leave. What if this hyperbolic trajectory is really a deceleration maneuver by technology beyond our detection? Imagine a civilization so advanced that mimicking natural orbital dynamics is child's play. A species that deploys surveillance assets disguised as comets, asteroids, even space debris. Perhaps 3I Atlas's unheard-of speed and strange chemistry aren't signs of alien formation, but of alien intention. As it nears perihelion, hidden systems might power up, preparing for whatever mission brought it here. Tonight, we step into the speculative shadows, where natural explanations falter and cosmic paranoia takes root. The question is not if 3I Atlas will leave, but whether we'll realize when it decides to stay. On July 1st, 2025, Chile's Atlas telescope detected a pinpoint of light with a hyperbolic trajectory, proof that it came from outside our solar system. Designated 3I Atlas, formerly C2025N1, it is humanity's third confirmed interstellar object, after Oumuamua in 2017 and 2I Borisov in 2019. But this visitor may carry implications far beyond the first two, implications that stretch the very meaning of a worst-case scenario. Unlike solar system constants bound by ellipses, 3I Atlas traces a hyperbola. Its orbital eccentricity exceeds 1.0, marking it as unbound to our Sun's gravity. Racing inward from the constellation Lyra at unprecedented speed, it will reach perihelion on October 29th at over 130 km/s, fast enough to cross the continental US in under 3 minutes. Yet beneath these mathematical certainties lies a nagging question. What if the worst case isn't where it's going, but what it might force us to confront? Despite its dramatic velocity, 3I Atlas poses no threat to Earth. Its closest approach in mid-December will be about 1.8 AU, roughly 270 million kilometers, nearly twice the distance between Earth and Mars at its nearest. NASA's stance is clear. This is a natural comet, not an alien spacecraft or dangerous object. Yet, when we slip beyond NASA's cautious language into speculation, what shadows could this ancient wanderer cast over our assumptions about intelligence, purpose, and coincidence? The Hubble Space Telescope has monitored the object since its discovery, observing classic comet behavior as solar radiation sublimates ices in the nucleus, forming a glowing coma. The James Webb Space Telescope captured spectra on August 6th, revealing unusually high CO2 concentrations, a chemical signature suggesting formation conditions unlike anything in our own solar system. This chemical oddity prompts an uncomfortable question. What if 3I Atlas's true significance lies not in what it is, but in what it forces us to confront about what we do not know? Ground-based observatories worldwide have joined the effort. Radio telescopes detecting only natural emissions, silent where artificial signals might hide. This global campaign exemplifies modern astronomy, confirming both the object's interstellar origin and its harmless path. But what if we push beyond harmless into scenarios that challenge not our physical safety, but our fundamental understanding of our place in the cosmos? The low frequency of such discoveries leads astronomers to assume these wanderers are debris, leftovers of planetary formation, flung into space by gravity from distant stars, destined to drift for eons. Each one teaches us something new about the galaxy beyond our sun's reach, while posing no real threat. But if the galaxy is full of these ancient messengers, what happens when we dare to speculate beyond scientific consensus? As The Guardian aptly put it, 3I Atlas is a cosmic curiosity, not a catastrophe. A reminder that we inhabit a universe far stranger, far more connected than daily life suggests. This visitor offers us a fleeting glimpse into galactic history, carrying secrets from stellar neighborhoods we can scarcely imagine. But perhaps the truest mystery is less about what secrets it carries, and more about what secrets it might unlock, about interstellar visitors. about intelligence, and about the speculative realms beyond reach of our telescopes. The raw numbers alone are staggering. 3E Atlas moves at over 130 km/h, roughly 150 times faster than a high-velocity rifle round. Its hyperbolic excess velocity, about 61 km/h, is what it retains even when solar gravity is accounted for. Unchanged by eons of galactic travel, its speed dwarfs its interstellar predecessors. Oumuamua traveled 26 kilometers. 2I Borisov 32 km/h. 3I Atlas's much higher velocity suggests either a violent ejection from its parent system or acceleration through multiple gravitational slingshots during its cosmic journey. But what if the seemingly increasing speeds of these interstellar visitors hint at something more deliberate than random cosmic violence? Something that nudges us into speculative domains beyond the reach of our instruments? Estimating its size is difficult because the glowing coma obscures the nucleus. Current guesses range from Micah 0.3 to 15.6 km in diameter, from 3 football fields to a small mountain. The uncertainty arises from our assumptions about reflectivity and coma efficiency. Lower estimates are more plausible given typical cometary behavior, but even at 0.3 km, it is a substantial body. Yet, what if that very uncertainty hides possibilities that transcend mere size? This ambiguity raises intriguing questions about survival. How could such a modest object survive violent ejection and billions of years in interstellar space? Smaller bodies are more vulnerable to tidal disruption or high-speed impacts with cosmic debris. But what if answering this survival puzzle points toward speculative ideas of durability, purpose, or design that challenge natural explanations? This visitor possesses extreme antiquity. Analysis suggests it came from the Milky Way's thick disk, a stellar population formed when the galaxy was young and chaotic. If true, this object might predate our entire solar system by billions of years, carrying within its nucleus a record of galactic evolution from an era when the universe was less than half its present age. But what if that ancient origin story serves as the foundation for speculative scenarios that challenge our notions of time, purpose, and cosmic intelligence? The thick disk interpretation arises from its motion relative to galactic rotation. While most local stars and objects share the galaxy's spin, 3I Atlas approaches from an unusual angle, hinting at membership in an older, more randomly oriented population, stellar seniors whose orbits haven't been tidied up by billions of years of galactic evolution. Yet, if we slip past pure astronomy into speculation, what might that odd approach suggest about intentional navigation or purposes beyond mere orbital mechanics? Despite its speed and arcane history, 3I Atlas presents no dynamical threat. Its hyperbolic path ensures it cannot be gravitationally captured. Its closest approaches to planets are measured in astronomical units, not kilometers. But as we peer beyond scientific certainty, what if the real worst-case scenarios aren't about collision, but about what this visitor might represent? Observation windows are limited. Its peak brightness is only magnitude Mach 11, demanding telescopes even in ideal conditions. During its closest approach to the Sun, it will vanish into the solar glare, precisely when it could become most active. That cosmic timing feels almost too convenient to be random. What if this observational limitation becomes the gateway to speculative ideas where what we cannot see is more important than what we can measure? What emerges is a portrait of cosmic endurance. Ancient, fast, fleeting. 3I Atlas sits at the intersection between impressive physics and subtle risk. It reminds us that the universe operates on scales far beyond daily life, even as the mathematics lets us predict its position years in advance. Yet when we dare to ask what lies beyond these trajectories, many speculative worst-case scenarios emerge, not about orbital mechanics, but about cosmic revelation. Part 4. Worst Case. Answered after thousands of words speculation, one might expect catastrophe. But the worst case often proves mundanely safe. There is no impending Hollywood disaster, No civilization-ending impact. No gravitational chaos sending Earth off its course. Cold, precise celestial mechanics instead deliver a verdict we can accept. 3I Atlas will not threaten us. Still, when we step beyond the safety of scientific certainty, speculative worst cases lurk not in physical harm, but in revelations we are unprepared for. Let's restate the key numbers. Closest approach to Earth, Glas Gunwan Twait, AU 270 million kilometers, more than twice the closest Earth-Mars distance. NASA Science was 1 perihelion, closest to Sun. Featured 1.4 AU, placing it between Earth and Mars orbits, enough solar heating and coma formation, but too distant to perturb planetary orbits. NASA Science plikut to Wikipedia plus to its hyperbolic speed ensures it cannot be captured into the solar system. It will pass through and leave. NASA Science plus to Wikipedia please. These aren't rough guesses. They come from orbital calculations that include gravitational influences, radiation pressure, even relativity. So when astronomers claim no threat, they speak from centuries of celestial mechanics and decades of tracking small celestial bodies. Yet here's the twist. What if those same calculations, what reassure us, are also the foundation for speculative worst-case scenarios not about collision, but about contact, communication, and cosmic revelation? What if the fact that 3I Atlas moves too fast to be captured is itself a clue, a design hint, a precise timing, a signature of purpose beyond our current detection or understanding? Scientific reality supporting observations. To ground speculation, here is what we do know from recent observations. Chemical composition. JWST spectroscopy shows a CO2-dominated coma with a CO2 H2O mixing ratio of about 8.0 plus 1.0, among the highest ever observed in any comet. ARC-CV water detection. Ultraviolet imaging from SWIFT revealed OH emission, a proxy for water, near 3.51 AU, implying a water production rate, under certain assumptions, of NAR 1.35 10^27 molecules per second, given pre-covery activity. NASA's test data suggests 3I Atlas might have been active even when 6.4 AU from the Sun, unusually distant for comet outgassing. AR-SIV polarimetry. Observations from VLT and other telescopes show a deep and narrow negative polarization branch. C. U 2.7%. At phase Taishwar 7 degree, a behavior uncommon for comets and indicative of a distinct surface or compositional structure. These empirical facts constrain speculation. Yes, its CO2 richness is extraordinary. And yes, its distant water activity is unusual. Those anomalies give fuel to your speculative ideas about internal mechanisms, hidden energy, or chemical messaging. But they don't prove anything except that 3I Atlas is a remarkable object requiring deeper study. Interstellar visitors often carry emotional weight quite apart from any real danger. Primitive parts of our brains respond instinctively when something unknown approaches, even though the actual geometry and scales of space usually make such encounters harmless. Space's vast distances and precise orbital mechanics tend to make encounters fascinating, not threatening. Yet, what if our focus on physical danger blinds us to other kinds of risk? Speculative scenarios where the worst case isn't what 3I Atlas might do to us, but what it might reveal about us, our assumptions, and our place in a universe far stranger than we can yet imagine. NASA's communications walk a delicate line. They acknowledge the scientific importance of the object while stressing that it poses no hazard. Their language is clear and jargon-free, helping the public find wonder in discovery without cultivating undue fear. History gives us precedent. Oumuamua in 2017 showed odd behavior but never threatened Earth. 2I Borisov in 2019 behaved like a conventional comet. 3. Atlas continues that pattern, scientifically intriguing, dynamically harmless. But what if this pattern of benign interstellar visitors is concealing something far more significant? A cosmic census, or a gradual revelation that compels us to reconsider everything we think we know about intelligence, purpose, and our cosmic neighborhood. Knowns, unknowns, and the shadow of possibility. Our current understanding provides a firm foundation. We know 3I Atlas's speed, trajectory, and its unusual CO2-rich composition. We have evidence that it is extremely old and may originate in the galaxy's thick disk. Multiple world-class telescopes have measured its chemical behavior and physical activity. These facts suggest an ancient, fast, chemically unusual, but fundamentally natural comet. Yet beneath those certainties lies a deeper mystery. What speculative scenarios emerge when we ask not just what 3I Atlas is, but what it might represent in a universe where intelligence could take forms beyond our imagination. Important unknowns remain. Its nucleus size is uncertain. Estimates range from hundreds of meters to several kilometers. We don't yet know whether CO2 dominance is a surface phenomenon or reflects its bulk, composition. We cannot yet trace its natal stellar system, nor reconstruct every gravitational encounter that shaped its current path. Crucially, none of these unknowns alter the risk assessment. They don't change the fact that there is no physical threat. But what if these uncertainties become the foundation for speculative scenarios that push us beyond the comfortable boundaries of natural explanation? This is precisely the distinction proper astronomical risk assessment makes, distinguishing scientific intrigue from real threats. So far, media coverage has adhered to a mature approach, emphasizing both the object's scientific value and its harmless nature. Hubble images show textbook cometary features. Webb spectra show unusual but plausible chemical compositions. Ground telescopes monitor expected emission variation. There is no detected artificial signal, no thermal signature of engineered systems, and no controlled maneuvers. Every measurement so far supports the conclusion that 3I Atlas is what it appears to be: a natural comet crossing through interstellar space, obeying universal physics. But might this absence of evidence for artificiality be a doorway rather than a barrier? What if intelligence so advanced could operate beyond our present tools' reach, so subtle that we mistake design for natural anomaly? Thus, for now, the worst-case scenario defined by measurable physical hazards is thoroughly debunked. The mathematics is solid, observations are consistent, conclusions reassuring. This cosmic visitor comes in peace, intentionally or otherwise. But that's exactly when we step beyond scientific consensus into the realm of pure speculation, where worst-case scenarios don't threaten our bodies. They challenge our understanding of what is possible. Part 5. Alien Technology or Comet. Now, we cross deliberately from established fact into speculation, where possibilities multiply like reflections in a hall of mirrors. What follows is a thought experiment, not scientific conclusion. The evidence strongly favors the natural comet hypothesis. NASA, ESA, and nearly every mainstream astronomy institution describe 3I Atlas as a comet. That's not mere conservatism. It's the best fit to the data. The object exhibits classic cometary behavior, follows predictable orbits, and shows spectral lines expected from sublimating ices. Occam's razor favors the natural explanation. Still, science has a history of surprises. Pulsars were once nicknamed LGM, Little Green Men, because their signals were regular and mysterious. Fast radio bursts puzzled astronomers until they revealed new classes of astrophysical phenomena. Could 3I Atlas become another instance where nature outstrips our first impressions? The speculation about artificial origins isn't conjured from nothing. Avi Loeb, the Harvard astrophysicist known for his provocative views on Oumuamua, has floated similar possibilities for 3I Atlas in interviews and blog posts. Importantly, he frames them as hypotheses, not assertions. His approach reminds us to remain open, not ungrounded. What would count as convincing evidence for artificial origin? Here are some possibilities. Coherent radio emissions, structured signals that couldn't arise from natural processes. Trajectory anomalies inconsistent with outgassing, i.e., acceleration or deceleration that doesn't match solar heating patterns. Brightness, light curve engineering, changes in luminosity over time inconsistent with natural sublimation and rotation, perhaps hinting at controlled orientation or active systems. So far, none of those signatures have appeared. Radio observatories hear only the silence of space and natural emissions from sublimating cometary material. The orbit matches celestial mechanics without unexplained deviations. Its brightness changes a line with rotating uneven surfaces and solar heating, exactly as seen in many comets. And the CO2-rich chemistry, though unusual, can be explained through natural processes. Formation near CO2 snowlines, radiation processing, dust mantles sealing volatiles, etc. Jumping from chemically odd to artificially engineered would require data that natural processes cannot account for. That's the burden of proof for extraordinary claims. We've seen the same dynamic with Oumuamua. Speculation ran wild, but no artificial signature held up. Ultimately, natural explanations prevailed once all data were in. That's the pattern. Remain open to surprises, but demand rigorous evidence. If media or popular presentations treat speculation as fact, they risk distorting public understanding. It's crucial to label such ideas clearly as speculation, not established science. That distinction matters deeply, both for this object and for how people perceive scientific method itself. Even while we entertain alternative ideas, it doesn't detract from how remarkable 3I Atlas already is, even as a conventional comet. It carries chemical and historical information from star systems we cannot yet visit, offers data about processes billions of years old, and expands our awareness of how diverse interstellar travelers might be. Remember, many of astronomy's greatest discoveries began as odd, unexplained signals. Quasars, gamma-ray bursts, gravitational waves, all began as mysteries before new physics or technologies made sense of them. Whether 3I Atlas is ultimately prosaic or exotic, it has already expanded our cosmic horizons. Now we descend into the most extreme realm of speculation, where the shadows of cosmic possibility stretch into scenarios that would fundamentally reshape how we see ourselves in the universe. What follows is pure thought experiment, a mental journey into implications and possibilities that current evidence does not support, but that help reveal the kinds of profound questions we might face if our assumptions about 3I Atlas turn out to be inadequate. The dark forest hypothesis comes from both science fiction and serious SETI discourse. It draws its name from Liu Cixin's novel The Dark Forest, but stands as a serious philosophical position in debates about alien civilizations. The idea says advanced civilizations might remain hidden from each other, assuming that revealing one's existence could invite destruction by a more advanced neighbor. In that kind of universe, silence is survival. To broadcast oneself is risky. So let us imagine, and emphasize again this is pure imagination, that 3I Atlas is not a natural comet, but a reconnaissance probe. If that were true, the implications would be staggering. We would be dealing with intelligences capable of engineering objects that can survive billion-year interstellar journeys, while maintaining near-perfect disguise as a comet. The sophistication implied by such a disguise would dwarf anything humanity currently knows. What such a probe would need to do to pass undetected, this probe would have to mimic every aspect of comet behavior convincingly pursued. Spectroscopic signatures that match natural, sublimating ices outgassing, patterns that respond precisely to solar heating surface, reflectance and physical properties consistent, with natural ices and dust-volatile inventory sufficient to maintain deception throughout its journey. Meanwhile, house sensors, systems, and communications hardware to justify the mission. The power requirements would be immense. To maintain active internal systems over interstellar distances and timescales of billions of years demands energy sources far beyond what we currently can build. Hypothetically, a radioisotope, thermoelectric generator operating over eons advanced, fusion reactors using trace interstellar hydrogen, harvesting energy from cosmic rays or magnetic fields along the journey, triggering. The scenario now lets imagine a turning point in the narrative. As we continue observing 3I Atlas, anomalies begin to appear, ones that defy natural explanation. Radio telescopes detect faint, structured transmissions as the object moves through the outer solar system. Its trajectory shows subtle but unmistakable course corrections. Inconsistent with outgassing, its chemical emissions display patterns too complex and organized to be random. Then, the most dramatic moment, 3I Atlas begins to deploy secondary probes. Smaller objects peel off and take positions around Venus, Mars in the asteroid belt, or at stable Lagrange points. Suddenly, our solar system is hosting a surveillance network of unknown origin and capability. Humanity's response faced with that scenario, the questions become overwhelming. Who speaks for Earth? The UN, space agencies, scientific institutions, individual nations? How do we respond? Do we try communication, remain silent, or hide? Would our response itself become data? In such a scenario, any act of ours, silence, announcement, probe, signal, could be read as intention and influence how the unknown intelligence reacts. The crisis communication challenges would be immense, informing the global public without triggering panic, balancing transparency with stability, admitting unknowns while retaining credibility. All of that under the burden that we might be dealing with a civilization far beyond our comprehension. Misinformation would become a battlefield. Distinguishing verified observations from speculation becomes crucial when the stakes might involve the future of human civilization itself. The mere suggestion of alien surveillance would spawn countless conspiracy theories, false flag accusations, and claims of government cover-ups, distinguishing legitimate scientific observations from baseless speculation would become crucial, especially when dealing with the most important discovery in human history. The technology implications would be equally profound. If 3I Atlas revealed capabilities beyond our current physics, it might offer insights into propulsion systems, energy generation, materials, science, or communication methods that could revolutionize humanity's technology, assuming the intelligence behind the probe allowed us to persist and develop. Perhaps the most unsettling aspect of this speculative scenario is its temporal implications. If 3I Atlas has been traveling for billions of years, it could represent technology from a civilization that achieved interstellar capability when our galaxy was very different. The intelligence that launched it might no longer exist. We might be interacting not with its creators, but with autonomous systems, ghosts of a lost civilization, carrying out programmed directives across deep time with mechanical precision and no living engineers behind them. Of course, and I repeat, none of this speculative narrative is supported by current observations of 3I Atlas. Every measurement, every spectral line, every image continues to support the natural comet hypothesis. The object behaves exactly as astronomical theory predicts a comet should. Its chemical signatures, while unusual, fall within plausible natural processes. Its trajectory obeys physics without needing exotic explanations. The value of this speculative exercise is not in its likelihood, but in how it illustrates how fast our cosmic perspective could shift if our assumptions fail. The universe has surprised us before and will again. It teaches us to maintain both healthy skepticism toward extraordinary claims and openness to possibilities beyond our current understanding. But as we push ever deeper into speculation, always remember we are exploring the landscape of possibility, not the terrain of established fact. The real 3I Atlas remains a fascinating natural phenomenon, ancient, fast, chemically unusual, but fundamentally comprehensible within our current scientific framework. Whether that understanding will suffice is an open question, one future observations must answer. Part 8. Great Filter Alarms, City Who's. Great Filter is one of the most profound ideas in the study of civilization and intelligence. If life should be abundant across the cosmos, why do we see no obvious signs of it? First framed implicitly by physicist Enrico Fermi, this question has led thinkers to propose that somewhere along the path from simple chemistry to starfaring civilization, there is a barrier so difficult or dangerous that almost no civilization passes it. If we entertain the possibility that 3I Atlas is engineered rather than natural, we must confront the fate of its maker. Its apparent age, possibly billions of years, places its origin deep in the galaxy's past, when stellar populations and cosmic conditions were very different from today. If this visitor is artificial, did its civilization survive to see it arrive? Or did that civilization succumb to its own great filter? The timescales involved are staggering. Human civilization, from agriculture through to the space age, spans mere thousands to centuries. But 3I Atlas, if artificial, would represent a technology surviving millions or even billions of times longer than our entire history. That draws our attention to the difference between technological longevity and biological survival. We must imagine engineering systems that remain functional across eons. Our most durable human structures, pyramids, monuments, radioactive isotopes, last thousands or millions of years. But sustaining electronics, propulsion, artificial intelligence across billions of years demands materials and systems we can scarcely imagine. It implies mastery at the atomic scale, energy systems beyond stellar lifetimes, and self-repair over cosmic time. A civilization that could build such artifacts would likely have solved many of the challenges that typically kill advanced civilizations. Yet here might be evidence of only their relics. Why then no sign of the civilization itself? If 3I Atlas is their only trace, it suggests the possibility that their creators succumbed to a great filter despite technological triumph. Some possible scenarios: they overconsumed their resources on a galactic scale, collapsing before expansion was stable. They encountered hostile intelligence or warfare that destroyed them. They succumbed to internal contradictions, societal breakdown, runaway technology, ecological collapse. Or perhaps they transcended themselves, evolved into forms invisible or irrelevant to our perception, uploading minds, merging with technology, ascending to higher dimensions or states undetectable by us. Our galaxy holds 400 billion stars, many much older than our Sun. Even if only a tiny fraction ever spawned technological civilizations, we might expect more evidence of them. The so-called Great Silence demands explanation. Current SETI practice reflects this uncertainty. Most efforts are passive, listening rather than broadcasting, under the assumption that advertising our existence prematurely may be dangerous. In the face of the dark forest idea, revealing ourselves may be unwise. The mere suggestion of alien surveillance would immediately spawn countless conspiracy theories, false flag accusations, and claims of government cover-ups. Distinguishing between legitimate, scientific observations and baseless speculation would become critical to preserving rational public discourse about what would easily be the most momentous discovery in human history. The technological implications would be just as profound. If 3I Atlas somehow revealed capabilities beyond our current physics, it could give us insights into propulsion systems, energy generation, advanced materials, or communication methods that would revolutionize human technology, assuming the intelligence behind it allows us to continue existing and developing. Perhaps the most unsettling aspect of this speculative scenario is the temporal dimension. If 3I Atlas has been traveling for billions of years, it may represent technology from a civilization that achieved interstellar reach when the galaxy was very different. The creators might no longer exist. We might be dealing not with living beings, but with autonomous relic systems. Ghost probes executing mission. Directives long after their civilization vanished. Of course, and this must always be emphasized, none of this speculation is supported by current observations of 3I Atlas. Every measurement, every image, every spectrum continues to support the natural comet hypothesis. The object behaves as theory predicts comets should. Its chemicals, trajectory, and outgassing patterns all fall within what natural processes can explain. The point of such speculative exploration is not to assert likely truth, but to show how drastically our cosmic perspective could shift if our assumptions fail. The universe has surprised us before, and almost certainly will again. This reminds us to hold healthy skepticism toward dramatic claims, but also openness toward possibilities beyond current models. As we trudge deeper into speculative territory, it becomes ever more essential to separate what we imagine from what we know. The real 3I Atlas is already extraordinary. Ancient, fast, chemically unusual, yet comprehensible within our current scientific framework. Whether that framework will remain adequate is an open question, one that future observations must resolve. Part 9. Fermi's Whisper. Where is everybody? This question echoes in every astronomical survey, haunts every SETI effort. If the galaxy should be brimming with intelligent life, then where is everybody? Enrico Fermi posed the question casually in the 1950s, but as our knowledge of the cosmos has grown, its implications have deepened. Interstellar objects like 3I Atlas deepen that mystery. Each such visitor is a natural experiment, a sample of matter from other star systems. In principle, some should carry signatures of technology, engineered materials, artificial isotopes, or patterns that betray intelligence. Yet, so far, all confirmed interstellar visitors appear wholly natural. That absence of artificial detection might itself tell us something profound about how advanced civilizations relate to interstellar space. Perhaps truly advanced societies prefer emissaries that are silent, probes designed to be indistinguishable from natural objects. If so, their sophistication makes them invisible to our current instruments, which are tuned to detect the obviously artificial. But that raises hard questions. If 3I Atlas were such a disguised probe, what observational evidence would ultimately reveal its true nature? We return to the boundary between natural and artificial phenomena in space, a boundary that may be far more subtle than we currently assume. Possible diagnostics of artificial origin. Narrowband radio emissions. Natural processes produce broad, incoherent radio noise. Artificial signals tend to concentrate power in narrow spectral lines or modulated patterns. So far, 3I Atlas is silent in narrowband observations. Only the expected emissions from cometary outgassing and interaction with the solar wind have been detected. Unusual thermal profiles. Natural bodies absorb sunlight and re-radiate heat following known physical laws. Artificial objects might display temperature gradients or anomalies inconsistent with passive heating, such as internal heat sources or asymmetric thermal control. Current infrared observations of 3I Atlas show thermal signatures consistent with natural heating of cometary materials, temperature rising predictably with solar approach, and heat distribution shaped by surface heterogeneity. Controlled maneuvers, perhaps the starkest signature. If the object exhibits non-gravitational accelerations that cannot be explained by gas outgassing, or maneuvers not aligned with solar heating patterns, that would strongly hint at active guidance systems. So far, none of these artificial signatures have been observed in 3I Atlas. Its trajectory obeys gravity. Its brightness variations align with natural rotation and sublimation. Its chemistry, while unusual, lies within what astrophysical models can explain. What current science tells us, anchored in observed data. To ground this speculative discussion, here are some of the key confirmed scientific findings about 3I Atlas orbital path and safety. It follows a hyperbolic trajectory. confirming it is not bound to the Sun and will approach no closer than Ryugang or 1.8 AU from Earth, far too distant to pose any threat. NASA science size constraints. Hubble imagery places an upper bound on its nucleus diameter at 3.6 kilometers, 3.5 miles, though it could be much smaller. NASA Science Chemical Composition (JWST) spectroscopy reveals a coma dominated by CO2, with a CO2 H2O mixing ratio 8.0 plus 1.0, one of the highest ever measured for a comet. Arxiv notes of water, CO, OCS, and dust are also present. Archiva +1. Water detection. Ultraviolet observations, SWIFT, detected OH emission at water 351. AU, implying a water production rate of MAU 1.35 and has 27 molecules per second. Arxiv polarimetric anomaly. Recent polarimetric studies show 3I Atlas has a deep and narrow negative polarization branch, 2.7% at ET or 7° phase angle, a behavior not seen in typical comets or asteroids, suggesting a possibly unique coma or dust structure. Arxiv spectral attributes. Optical and near-IR spectra show a red slope and features consistent with mixtures of dust and water ice, ET akin to D-type asteroids combined with ices. R-XAV cometary activity at large distance. The comet is active already at 3Q AU, well beyond Mars, which is unusual, indicating volatile behavior beyond normal comet expectations. Arcuev, Pruum. All these observations support the natural comet model, though with some surprising chemical and physical oddities that inspire deeper inquiry. Natural objects in space follow trajectories dictated by gravity and occasional tiny thrusts from outgassing. These non-gravitational accelerations are usually small, random in direction, and correlate closely with measures of comet activity, coma brightness, gas production rates, etc. An artificial probe, by contrast, might show controlled course corrections, intentional velocity changes, or trajectory adjustments to serve mission goals. Distinguishing those from chaotic forces produced by asymmetric outgassing would be challenging, but persistent patterns of control could eventually become detectable with high-precision astrometric data. So far, 3I Atlas has shown no signs of controlled maneuvers. Its path traces a smooth hyperbolic arc predicted by gravitational models, with only minor perturbations matching expected effects of solar radiation pressure and cometary outgassing. If it does have propulsion systems, they remain dormant or so subtle that current observations can't pick them out. The natural explanation for interstellar objects like 3I Atlas fits well with theoretical models of planetary system formation. Simulations show that early in a system's life, gravitational interactions can sling many objects out of their home systems, rocky and icy debris that never become full planets. The galaxy should thus contain a vast population of such nomads. From that view, Oumuamua, 2I Borisov, and now 3I Atlas are the first discovered examples of a much larger class. In fact, surveys like Vera Rubin Observatory, once active, are expected to detect interstellar objects at rates of several per year, converting them from odd curiosities into routine astronomical discoveries. This statistical view offers one answer to the Fermi paradox, or Fermi's question. If natural ejected bodies exist in vastly greater numbers than any engineered probes, artificial signatures might be hidden in a sea of natural. Wanderers, a needle in a haystack problem of extreme difficulty. The chemical diversity exhibited by 3I Atlas, especially its CO2-rich coma, adds nuance to that statistical picture. It shows that not all interstellar objects will mirror comet chemistries familiar to us. As our sample size increases, we may find that what once looked anomalous or possibly artificial is simply part of the natural variety of planetary formation outcomes across the galaxy. Be warned, survey bias complicates all this. Our telescopes and detection methods favor certain trajectories, brightnesses, and sky directions. The few interstellar visitors we've seen might not represent the broader population at all. The fact that 3I Atlas came from the southern skies in an unexpected direction suggests our models of interstellar object distribution are still incomplete, or that gravitational encounters can scatter individual objects enough to mask their origin. In coming years, better observational tools will sharpen our view. The Vera Rubin Observatory will build a statistical catalog. Infrared space telescopes will measure thermal emission and composition with high precision. With large data sets, we'll see whether interstellar objects follow predictions, or whether anomalies emerge that demand exotic explanations. If alien probes hide among the natural population, eventually persistent deviations from natural behavior, minute but systematic, might betray them. But until then, the absence of evidence must not be overinterpreted. Every natural interstellar object we study reinforces the hypothesis that intelligences capable of interstellar engineering either don't exist or are extremely rare, remain undetectable by our present technology, or avoid revealing themselves via obvious signatures. But absence of evidence is not proof of absence, especially when our detection capabilities are limited and samples are few. 3I Atlas. Whether natural or artificial is another piece in humanity's quest to define its place in the cosmic community. As we push deeper into speculative scenarios, the contrast between what we observe and what we imagine becomes ever more important. The real cosmos, revealed through patient observation and rigorous analysis, is already strange and wondrous, without needing ungrounded additions. Whether that strange reality includes other intelligences is an open question, but one future observations must answer. Part 10. Cinematic Worst. Silent Invasion via Microseeds. Now we enter pure speculative theater, where plausible science fiction bleeds into imaginative extremes. Think of this as the outer boundary of possibility. These ideas stretch or suspend known principles, but try to retain some connection to physics so they remain thought-provoking. Imagine, 3I Atlas is not just a probe, but a delivery system, harboring microscopic devices or even engineered microseeds, dormant until environmental triggers awaken them. These could be nano-engineered systems or synthetic, hardy biological entities designed to survive the rigors of interstellar space for eons. This notion has precedent in the panspermia hypothesis, life spreading via comets, asteroids, though what's suggested here is more ambitious. These microseeds might remain inactive until they detect technological signatures, radio emissions, pollution, city lights, and then activate. Or maybe they respond to solar radiation thresholds, awakening as their host object enters a star system with the right spectral characteristics. But the engineering demands would be staggering. These micro-machines would have to resist cosmic radiation, micrometeoroid impacts, and extreme temperature swings over billions of years. They'd need power sources lasting far beyond any we can plausibly build, information storage systems stable on cosmic time scales, and perhaps the ability to bootstrap more complex structures from raw material near their destination. If such technology were possible, the strategic implications are chilling. A single interstellar object could seed billions or trillions of micro-devices across a star system. The invasion, if one can call it that, would be silent, latent, and invisible until activation. Perhaps it would wait centuries or millennia before awakening, aligning activation with a civilization's development level, atmospheric changes, radio emissions, or other markers. Yet this scenario collides head-on with physical constraints. The environmental stress of cosmic radiation alone over long durations is likely fatal to molecular structures. The violent outgassing events that convert the comet into a visible object would subject embedded seeds to massive forces, scattering and destroying many. Even if some survived, The enormous dilution over interplanetary distances means few, if any, would ever reach Earth. The minimum approach distance, 1,8 AU, further weakens any chance of direct transfer. Existing planetary protection protocols assume sample returns and known contamination risks, not a passive drip of microscopic devices over astronomical distances. Detecting such seeds would be like finding needles across the entire volume of the solar system. Radar, optical, or infrared systems are simply incapable of reliably detecting micrometer-scale objects in space. The resources needed to monitor all space around Earth for such seeds would be enormous. Furthermore, from an engineering logic standpoint, such a strategy is wildly inefficient. If a civilization is capable of interstellar missions, more direct means, probes, communication bursts, physical spacecraft, would make more sense. The complexity, delay, and uncertainty of microseed spreading make it a less plausible tactic than other methods. Still, this scenario serves as a cautionary illustration of how imagination can outstrip plausible reality. It reminds us that in wrestling with cosmic mysteries, our fear or awe can lead us to hypothesize beyond what physics or reason supports. Natural objects in space follow paths ruled by gravity and occasional thrusts from outgassing. These non-gravitational accelerations are usually small, random, and correlate with comet activity, coma brightness, gas production, etc. An artificial probe, in contrast, might show controlled course changes, intentional velocity shifts, or trajectory tweaks for mission goals. Distinguishing those from chaotic outgassing requires long, precise tracking, looking for persistent patterns beyond what gas jets could explain. So far, 3I Atlas has not shown any controlled maneuvers. Its trajectory matches the smooth hyperbolic path predicted by gravitational models, with only small deviations consistent with solar radiation pressure and outgassing. If it has any propulsion, it's either inactive or too feeble to detect given current precision. The natural object hypothesis fits well with theories of planetary system formation. Simulations suggest that young planetary systems eject large amounts of rocky and icy debris when planets migrate or gravitationally interact. Many small bodies could get flung into interstellar space. From this perspective, the interstellar visitors we've seen, Oumuamua, 2I Borisov, now 3I Atlas, are the leading edge of a much larger population. Modern surveys expect we'll detect many more interstellar objects in coming years. Indeed, scientists predict that telescopes like the Vera Rubin Observatory will find multiple such visitors per year, shifting them from curiosities to routine objects of study. Sky at Night Magazine, this. Statistical argument also provides a partial answer to the Fermi paradox. If natural ejected bodies are far more numerous than any engineered probes, then artificial signatures would be hidden in a sea of natural ones, a needle in a haystack problem of extreme difficulty. The chemical diversity of 3I Atlas further complicates things. Its CO2-dominated coma is unusual. The CO2-H2O mixing ratio is 8.0 plus 1.0, one of the highest ever measured in a comet air skew. As our sample of interstellar objects grows, we may find that what seems anomalous is simply part of a normal cosmic variety in comet chemistry. But caution is needed. Our observations suffer from survey bias. We preferentially detect objects arriving from certain directions, with certain brightnesses or favorable geometries. The 3 interstellar visitors we have may not reflect the whole population. In fact, 3 Atlas's trajectory, coming from an unexpected direction in the southern sky, surprised some astronomers, suggesting that our models of interstellar object distribution need refinement. NASA Science +1. In coming years, better surveys and instruments will sharpen the picture. The Vera Rubin Observatory will build a large statistical sample. Space-based infrared telescopes will measure thermal emission and composition in unprecedented detail. With large data, anomalies will either become explained or demand exotic hypotheses. If alien probes truly hide among this population, subtle but consistent deviations from natural behavior might eventually reveal them. But absence of such signals so far reinforces the conservative view. Either interstellar intelligence is rare, undetectable by current means, or deliberately hides itself. Yet absence of evidence is not evidence of absence, especially when our sampling is small and our detection limits limited. 3-eye atlas, whether natural or artificial, is another data point in humanity's attempt to understand our place in the cosmos. As we explore speculative possibilities, the contrast between observation and imagination grows ever more important. The real universe, revealed through patience and measurement, is already stranger and more beautiful than many fiction scenarios. Whether it includes other intelligences is a question for future discoveries and evidence. Part 10. Cinematic Worst. Silent Invasion via Microseeds Now. We enter the frontier of speculation, where plausible science borders imaginative fiction. What follows is extreme, but attempts to stay tethered to some physical principles. Suppose 3-eye atlas is not just a probe, but a delivery vehicle carrying microscopic devices or engineered microseeds, dormant until triggered by environment or signals. These seeds might be nanomachines or synthetic biological systems designed to survive interstellar travel for eons. While reminiscent of panspermia theories, life spreading via comets, this idea is more ambitious. These seeds might activate only when they detect technological signatures, radio emissions, pollution, changes in atmosphere, or respond to specific solar radiation thresholds when entering a star system. But the engineering burdens are enormous. These micro-devices would need to survive cosmic radiation, micrometeoroid impacts, extreme temperature swings over billions of years. They'd require power systems lasting far longer than stars, data storage stable over cosmic timescales, and perhaps the capability to bootstrap complex systems from raw materials once activated. If such technology existed, the strategic implications are chilling. One interstellar object could plant billions of microseeds across a target system. The invasion would be silent, latent, almost invisible until activation. Activation might wait centuries or millennia, timed to a civilization's development, atmospheric changes, or detectable signals. Yet this scenario collides with physical constraints. Long exposure to cosmic radiation would likely degrade many structures. The violent outgassing that gives comets their visible comas would likely destroy or scatter many embedded seeds. And any seeds that survive must travel from 1.8 AU distance, the comet's closest approach to Earth, across millions of kilometers, a huge dilution problem. Existing planetary protection protocols assume sample returns and known contamination, not minute passive intrusion across interstellar scales. Detecting such microseeds would be like searching for individual grains across the volume of the solar system, a practically impossible task with present technology. From an engineering logic perspective, this strategy is extremely inefficient. If a civilization is capable of interstellar missions, more direct methods, probes, signals, spacecraft, would likely be preferable. The complexity, delay, and uncertainty inherent in microseed systems make them less plausible than more conventional or direct approaches. Nevertheless, the scenario has value. It tests our imaginative boundaries. It reminds us how speculation can run beyond what physics or reason supports. In wrestling with cosmic mysteries, we must always keep clear the line between what evidence supports and what we imagine. These experiences have taught both scientists and science communicators the critical importance of separating intriguing observations from definitive conclusions. If humanity were ever to confirm the existence of alien technology, media management would become a central part of the response. The 24-hour news cycle's hunger for dramatic headlines could easily overwhelm careful scientific analysis, amplifying speculation and misinformation. Social media platforms would struggle to distinguish legitimate updates from verified sources against an inevitable flood of conspiracy theories, hoaxes, and misinterpretations. The economic implications alone would justify careful preparation. Global financial markets would likely experience severe volatility as investors tried to factor in the consequences of confirmed alien technology. Entire industries could face existential challenges if alien science offered revolutionary alternatives to current methods of energy production, transportation, or manufacturing. The stability of the global economy might depend on how effectively institutions manage the transition from speculation to confirmed reality. Educational institutions would also feel immediate pressure to adapt. Universities would be forced to revise curricula, research priorities, and even the most fundamental assumptions about humanity's place in the cosmos. The philosophical consequences would ripple outward through every academic discipline: astronomy, physics, anthropology, theology, political science, and beyond. Institutions that have spent centuries focusing on terrestrial phenomena would suddenly be challenged to incorporate non-human intelligence into their models of reality. The urgency of this task would be sharpened by the timeline constraints of interstellar visitors like 3I Atlas. Unlike most astronomical phenomena that can be observed and studied over long timescales, objects arriving from interstellar space move on trajectories determined by physics, not human convenience. They arrive and depart rapidly, leaving only months, not years, for meaningful investigation. This compresses normal decision-making processes into unusually short time frames, challenging the capacity of institutions to respond. Yet, the actual response to 3I Atlas has demonstrated remarkable efficiency. The global astronomical community identified the object, confirmed its interstellar origin, coordinated multi-wavelength observations, and began detailed analysis within weeks of discovery. This track record suggests that existing institutions and procedures, while imperfect, already provide a solid foundation for handling even unprecedented discoveries. The theoretical framework for responding to confirmed alien contact has been evolving for decades through the work of SETI researchers, astrobiologists, and international legal scholars. While no amount of preparation could anticipate every possible scenario, these efforts provide useful starting points for the kinds of rapid decisions that extraordinary circumstances would demand. Most importantly, the response to 3I Atlas has emphasized curiosity over fear, scientific investigation over speculation, and international cooperation over secrecy. These values, embodied in the transparent sharing of observational data and the collaborative nature of the research, represent humanity's best approach to cosmic mysteries. Whatever their ultimate explanation, the real-world response demonstrates that we already possess the technical expertise and institutional structures to investigate unprecedented phenomena effectively. Whether those same capacities would prove adequate for a genuine first contact scenario remains an open question. Still, the coordinated, professional response to 3I Atlas provides reason for optimism about our species' ability to face even more extraordinary cosmic encounters. As we move from speculative scenarios about alien contact toward more grounded discussions of scientific method and cosmic perspective, the 3I Atlas case serves as a template. It illustrates how modern civilization approaches the unknown, with technology, coordination, and intellectual curiosity. These qualities will remain our most reliable tools for engaging with mysteries that may one day reshape our understanding of our place in the universe. Part 12. Containment or Curiosity, the Chichu-E. Question of how to balance scientific curiosity against hypothetical risk reflects one of the oldest tensions in human exploration. It is the same drive that pushed us to cross oceans, climb mountains, and venture into space despite the dangers involved. In the case of 3I Atlas, this balance has tilted decisively toward curiosity, and for good reason. The object's trajectory and properties eliminate most conceivable containment scenarios while Maximizing opportunities for discovery. Current planetary protection protocols, developed over decades of space exploration, already provide frameworks for considering contamination risks in both directions, protecting Earth from alien microorganisms and protecting other worlds from terrestrial life. However, these protocols were primarily designed for direct sample return missions or spacecraft encounters, not for interstellar objects that pass through our solar system at safe distances while showing no evidence of biological activity. The fundamental principle of planetary protection rests on risk assessment and proportional response. For example, when NASA's Perseverance rover collected samples from Mars, extraordinary precautions were planned for their eventual return to Earth, ensuring that any hypothetical Martian microorganisms would not escape into our biosphere. In contrast, 3I Atlas poses no comparable risk, and thus, the correct balance leans toward maximizing observation and scientific insight rather than containment. Humanity has always been cautious when it comes to protecting alien worlds from contamination. Spacecraft headed toward potentially habitable moons like Europa go through intense sterilization procedures, their surfaces scrubbed and baked to prevent even a single microbe from hitching a ride. But 3I Atlas, our current cosmic visitor, presents a completely different scenario. Its closest approach to Earth is a comfortable 1.8 astronomical units, roughly 270 million kilometers away. At that vast distance, there's no risk of any material exchange with our planet. No interception mission is being planned. None could be, given its breathtaking velocity and the technological limits of our spacecraft. In this case, the idea of containment isn't even on the table. That freedom from physical danger has allowed something remarkable to unfold. One of the most open and collaborative global scientific efforts in modern history. Data from the Hubble Space Telescope, the James Webb Space Telescope, and dozens of ground-based observatories have been uploaded into public archives, accessible to anyone with an internet connection. Professional astronomers, graduate students, and even skilled amateurs have been working side by side, examining the same data, running their own analyses, and checking each other's conclusions. It's science at its best, transparent, rigorous, and beautifully democratic. This culture of openness has become one of astronomy's most powerful tools. The Mikulski Archive for Space Telescopes has made Hubble and Webb data freely available, turning what used to be exclusive information into a public treasure. The European Southern Observatory maintains its own archives, and citizen scientists contribute light curves, images, and measurements through platforms like Zooniverse. It's a global orchestra of curiosity, and everyone is invited to play a part. And this openness matters because secrecy is often the default response when humanity faces the unknown. Governments and intelligence agencies might lock away information about potential alien contact, fearing panic or misuse. But the scientific community has chosen the opposite path: transparency by default. Part of this is practical. Peer review demands data sharing. But part of it is philosophical. Science, at its core, belongs to everyone. The investigation of 3I Atlas is a case study in how these principles work in practice. Researchers from every continent have been coordinating observations in near real time. When new images come in from Webb or Hubble, they're not hidden. They're posted for the world to see. And while the internet can spread confusion as easily as knowledge, this collaborative approach has kept the signal louder than the noise. That's not to say misinformation hasn't tried to creep in. Social media, driven by algorithms that prize drama over accuracy, has amplified sensational claims and conspiracy theories. Some sources have exaggerated preliminary findings, or suggested shadowy government cover-ups of alien technology. But professional astronomers have responded with calm explanations, emphasizing that Atlas's strange behavior, its swelling green coma, its tail that seems to point toward the sun, still fits within the rules of comet physics. Visuals play a huge role here. Hubble and Webb images are stunning, almost otherworldly, and when processed to reveal fine details, they can look like science fiction artwork. Communicating them responsibly means framing them carefully. showing that these glowing plumes are chemical signatures, not spaceship exhaust. Interestingly, the question of containment has taken on a new meaning, less about trapping a physical object and more about controlling information. Should humanity ever classify certain discoveries, keeping them from public view? The consensus from the scientific community has been a resounding no. History has shown that openness benefits everyone. The discovery of pulsars in the 1960s, initially nicknamed LGM for Little Green Men, was eventually revealed to be natural physics, not alien beacons. The famous "wow" signal from 1977 is still publicly available for anyone to analyze. Even Oumuamua, another interstellar visitor with bizarre characteristics, was studied in a spirit of global collaboration, not secrecy. Citizen science has been critical to the Atlas story as well. Amateur astronomers with modest telescopes have captured light curves and images that complement professional observatories. Their contributions expand the dataset, helping build a more complete picture of this icy wanderer. It's hard to imagine that happening in a world where discoveries like this were locked behind classified walls. Looking ahead, new tools are on the way that will make this kind of collaboration even more powerful. Missions like SphereX will provide wide-field infrared surveys, mapping objects like Atlas in exquisite detail. The upcoming Vera Rubin Observatory's Legacy Survey of Space and Time is expected to discover hundreds of interstellar visitors over the next decade, allowing us to build statistical models of where these objects come from and how often they appear. This will either confirm that Atlas-like objects are a natural part of galactic evolution or reveal something far stranger. The institutional approach shaped by Atlas, rapid coordination, transparent data sharing, international cooperation, sets the stage for handling even more mysterious discoveries in the future. If we ever do find something genuinely anomalous, we'll have a blueprint for how to study it together. Perhaps the most profound contribution of Atlas is educational. It shows the public how science works in real time, the careful balance between skepticism and curiosity, the willingness to follow evidence wherever it leads, the refusal to jump to conclusions without extraordinary proof. Atlas has reminded us that science is not about instant answers, but about a process, a conversation with the universe that rewards patience. And then there's the cosmic perspective. Thinking about where Atlas came from is humbling. If its origins lie in the Milky Way's thick disk, then this object began its journey billions of years ago, long before our sun was born. Entire generations of stars have formed and died while it wandered through interstellar space. Massive suns exploded as supernovae, seeding the galaxy with heavy elements that would eventually form planets, oceans, and life, including us. To grasp the scale of its journey is to step outside human time entirely. If Atlas has been traveling for 5 billion years, that's 1,000 times longer than complex life has existed on Earth. While it drifted through the void, Earth saw the Cambrian explosion, the rise and fall of dinosaurs, 5 major mass extinctions, and finally, the emergence of humans who could look up and wonder. To Atlas, all of human history, every battle, every poem, every discovery has taken place in the last fraction of a cosmic second. And yet, despite the staggering timescales and distances involved, here it is, visible to our telescopes glowing green against the stars, whispering its story across the gulf of space. Its visit reminds us how small we are, but also how connected we are to the wider galaxy. We, too, are made of ancient stardust, products of the same processes that launched Atlas on its epic journey. In the end, 3i Atlas is not just an object to study. It is a mirror showing us how we respond to the unknown. Do we panic or do we explore? Do we lock information away or do we share it freely? The story so far suggests that humanity has chosen curiosity over fear, collaboration over secrecy. If more interstellar visitors arrive in the years ahead, and they surely will, Atlas will have prepared us to meet them with open eyes, ready to listen. Humanity has always been cautious about exploring the cosmos. Whenever we send a spacecraft toward worlds that might harbor life, like Europa or Enceladus, those probes are scrubbed, sterilized, and heat-treated until they're as clean as human technology can make them. The goal is simple: avoid contaminating alien ecosystems with terrestrial microbes. But with 3i Atlas, this elaborate caution is unnecessary. This interstellar visitor will never come close enough to touch us. Its nearest pass will keep it a comfortable 1.8 astronomical units away, roughly 270 million kilometers. No spacecraft interception has been planned, nor could one realistically be attempted at its current breakneck speed. This object is simply too fast, too far, too fleeting. And that distance has created a unique opportunity: the freedom to observe without fear, to study without worrying about containment. What followed has been one of the most open, collaborative, and democratic scientific investigations in recent history. Images from Hubble, spectroscopic data from the James Webb Space Telescope, and observations from ground-based instruments have been deposited in public archives, free for anyone to analyze. Astronomers on every continent, professionals, students, and amateurs alike, are poring over the same data, running their own calculations and checking each other's work. It is science at its purest, transparent, collective, and rigorous. This open-access approach represents a quiet revolution in how humanity does astronomy. The Mikulski Archive for Space Telescopes has made Hubble and Webb data available to anyone with an internet connection. The European Southern Observatory maintains similar databases, and amateur astronomers contribute their own light curves through citizen science platforms. A generation ago, such participation would have been impossible. Today, it is the norm, and this openness stands in stark contrast to how societies often respond to uncertainty. Governments might have locked away such information, treating it as a potential threat or intelligence matter. Instead, scientists have chosen transparency by default, partly because peer review demands it, but also because science belongs to everyone. Knowledge, like starlight, is meant to be shared. The study of 3i Atlas has become a model of how to balance skepticism with curiosity. Researchers acknowledge its oddities, its expanding green coma, its tail pointing sunward rather than away, but they explain these features within the well-tested physics of cometary behavior. The Internet, of course, has amplified wilder interpretations, claims of alien probes, government cover-ups, or secret missions. But professional astronomers have countered misinformation with patient explanations and open data, allowing the truth to outshine the noise. The images themselves have played a double role, both inspiring and misleading. Hubble's views of Atlas are breathtaking, glowing emerald clouds stretched across the darkness of space. To the public eye, they can seem almost alive, like science fiction artwork. Communicators face the challenge of presenting these visuals in ways that emphasize their scientific significance rather than sensational mystery. Interestingly, the idea of containment has shifted from the physical to the informational. Should some astronomical discoveries be restricted or classified? Most scientists argue no. Past precedent supports openness. Pulsars, once humorously nicknamed "little green men," were quickly revealed to be neutron stars. The famous "wow" signal remains publicly archived for scrutiny. Even the bizarre visitor Oumuamua was studied through an international transparent collaboration rather than a classified research effort. Citizen scientists have been vital to the Atlas investigation. Amateur telescopes across the world have contributed valuable images and timing data that complement professional facilities. This democratization of discovery would be impossible under a containment-first policy, but has proven enormously valuable for real science. Looking ahead, our observational capabilities are about to expand dramatically. Missions like SphereX will map the sky in infrared, while the Vera Rubin Observatory's legacy survey of space and time will detect hundreds of interstellar visitors over the next decade. For the first time, humanity will be able to treat such objects statistically, measuring how common they are, what they are made of, and what that tells us about planetary formation across the galaxy. If Atlas is a messenger, it is one of many, and soon we will have an entire chorus of wanderers to study. But Atlas is not just an object of observation. It is a witness to the history of the galaxy. Its journey likely spans billions of years, during which it may have passed close to hundreds or thousands of star systems. Each encounter would have been silent and unobserved, occurring in the depths of interstellar space. Each gravitational brush may have added or subtracted a sliver of momentum, like a cosmic game of pinball. Over millions of years, these small nudges could have accelerated Atlas to its present incredible velocity. And this is not just an object of rock and ice. It is a time capsule. Its chemistry, unusually rich in carbon dioxide, may reflect the conditions of a very different kind of star-forming region than the one that birthed our Sun. The molecules it carries are relics of ancient stellar neighborhoods, physical samples from places we may never visit. In this way, Atlas delivers not just data, but matter, alien isotopes, volatile inventories, mineral compositions that allow scientists to reconstruct the conditions of its birth. This is chemical archaeology on a galactic scale. Thinking about Atlas in this way highlights how small our own signal to the galaxy really is. Since Marconi's first radio transmissions in the late 19th century, humanity's electromagnetic bubble has been expanding outward at the speed of light. Today, it reaches only about 120 light-years into a galaxy 100,000 light-years across. Out of roughly 400 billion stars, only a few thousand lie within this sphere of detectability. To imagine that Atlas was somehow drawn here by our transmissions is implausible. Our presence is too young, too quiet, and too small. This perspective also reframes the so-called Great Silence of the cosmos. The Fermi paradox asks why, in a galaxy that should contain billions of habitable worlds, we do not detect signs of other civilizations. The answer may be as simple as scale. Even if thousands of civilizations exist, their signals would be extraordinarily faint and easily lost in the cosmic noise. Broadcasting a signal powerful enough to be easily detected across interstellar distances would require energy outputs comparable to entire stars. The challenge of communicating or traveling between stars may be far greater than we often imagine. And yet, the galaxy itself offers a solution to the challenge of speed. Atlas's incredible velocity was not generated by engines or propulsion systems, but by gravity itself, acting over vast stretches of time. Each stellar flyby gave it a tiny boost until, millions of years later, it arrived here moving faster than any spacecraft humanity has ever built. In a way, Atlas demonstrates that the Milky Way itself can act as a natural particle accelerator, flinging objects from star system to star system. Statistically, this means there are likely trillions of objects like Atlas wandering between the stars, frozen emissaries from their birthplaces. The Rubin Observatory is expected to discover several per year, which is still only a tiny sampling of the true population. Future discoveries may reveal objects with even stranger chemistries or trajectories, forcing us to refine our models of galactic evolution. Perhaps most profound of all is the time scale. If Atlas really does hail from the Milky Way's thick disk, it is a survivor from an era when the galaxy was young and violent, when stars formed in chaotic bursts and planetary systems were frequently disturbed. Its presence here tells a story not just of where it came from, but when, a story that predates our Sun, our Earth, and even life itself. During its billions of years of travel, entire stellar generations have come and gone. Massive stars have exploded as supernovae, seeding space with the heavy elements that would later form planets and oceans. Whole biospheres may have arisen, flourished, and perished, their lights burning and going out without Atlas ever slowing its journey. Meanwhile, Earth saw the Cambrian explosion, the rise and fall of dinosaurs, the appearance of humans, yet all of that occupies only the final fraction of a second in Atlas's multi-billion-year voyage. This is what makes Atlas so powerful as a symbol. It reminds us that we are latecomers to the story of the galaxy, but we are now capable of reading its oldest chapters. Its green glow against the starry sky is more than a cometary display. It is a message from the deep past, a piece of the galaxy itself that has wandered into our neighborhood. And as we point our telescopes toward it, we are reminded of what kind of species we can be: open, curious, collaborative. Atlas will leave us soon, disappearing back into the dark. But it will not leave us unchanged. It has shown that humanity can approach the unknown not with fear, but with wonder. It has proven that science, when shared freely, can unite people across nations and continents in a common quest. And it has reminded us that even in a universe vast enough to make us feel small, we are capable of noticing, of understanding, and of marveling at the beauty that drifts in from the stars. 3. Atlas is not just an interstellar object. It is a messenger from the deep past, a witness to epochs of galactic evolution, and a silent traveler whose journey tells a story far older than Earth itself. For billions of years, it must have wandered the Milky Way, slipping past star systems, each encounter slightly nudging its trajectory. Every gravitational interaction gave it a small push, adding or subtracting just enough kinetic energy to alter its course. Over cosmic time, those countless encounters became a grand pinball game played across the galaxy, accelerating this ancient wanderer until it reached the astonishing velocity we measure today. Its chemistry, rich in carbon dioxide, carries clues to its birth environment, clues that suggest it formed around a star very different from our Sun, in conditions unlike anything we have directly observed. Perhaps it came from a system where the architecture of planets, the composition of the interstellar medium, and the nuclear fusion processes inside the parent star all produced a unique chemical fingerprint. 3. Atlas is a time capsule of alien chemistry, carrying molecular signatures from neighborhoods of the galaxy we may never visit. When astronomers study such an object, they are not just observing from afar. They are, in a sense, holding a physical piece of another world in their hands. Not literally, but through the light that reveals its isotopic ratios, mineral composition, and volatile inventory. Each spectral line becomes a page in a book that was written billions of years ago, when the galaxy was younger, less metal-rich, and full of raw potential. This is chemical archaeology on a galactic scale, offering direct insight into processes we cannot otherwise witness. Against this grand backdrop, humanity's own presence in the galaxy seems impossibly small. Since Marconi's first wireless transmission in the late 19th century, our radio bubble has been expanding outward at the speed of light, now reaching stars within about 120 light-years. At first glance, this seems impressive, until we remember that the Milky Way spans roughly 100,000 light-years across. Our electromagnetic footprint is nothing more than a faint ripple in an ocean that holds 400 billion stars. To think that 3 Atlas was somehow drawn here by our signals is implausible. The object is far too old, its journey far too long, and our radio presence far too tiny to account for its arrival. This perspective helps explain the great silence that underlies the Fermi paradox. If the galaxy holds thousands of civilizations transmitting across the electromagnetic spectrum, their signals would still be vanishingly faint by the time they reached us. The inverse square law is unforgiving. Double the distance and the signal strength falls to a quarter. Interstellar communication would demand energy outputs rivaling small stars just to be easily detectable. Even with highly directional transmissions focused like a searchlight, the power requirements would dwarf anything humanity can currently generate. The same is true for interstellar travel. Accelerating even a small probe to a significant fraction of light speed would require energy comparable to the total annual output of industrialized nations. Larger spacecraft would require energy on a scale that exceeds our entire planetary capacity. And yet, 3 Atlas shows us that the galaxy has been solving this problem all along, using gravity itself as the engine. Each close stellar encounter was a free slingshot, and given enough time, nature accelerated this object to a velocity we could never hope to achieve artificially. At least not yet. Statistically, if planet formation routinely ejects debris into interstellar space, the galaxy should be filled with trillions of such wanderers. The Rubin Observatory will soon make the detection of several interstellar objects per year routine. Far from being a once-in-a-century curiosity, 3 Atlas may be just the first of a long line of messengers passing through our cosmic neighborhood, each bearing unique chemical and physical secrets. Some may be even stranger, with unusual compositions, extreme trajectories, or properties that force us to revise our theories about how planetary systems form and evolve. Time adds another layer of meaning to this discovery. The chemical composition of the galaxy has changed steadily over billions of years, as successive generations of stars fused hydrogen and helium into heavier elements, then scattered them into space through supernova explosions. If 3 Atlas is as ancient as our age estimates suggest, then it is a fragment from an era when the galaxy was chemically younger, poorer in metals, and governed by very different thermal conditions. Its carbon dioxide-dominant composition might have been common back then, only appearing rare today because the galaxy has evolved. Studying such objects is like holding a fragment of cosmic history in our hands, a direct look at what the universe was like before our solar system even existed. And now, as we approach the conclusion of this investigation, we find that the greatest gift 3 Atlas offers humanity is not fear or danger, but reassurance. In an age of global crises and uncertainty, there is something profoundly comforting about a cosmic visitor that arrives exactly when predicted, behaves exactly as physics says it should, and departs without incident. It is a reminder that the universe is not arbitrary or capricious. Its laws hold true across billions of kilometers and billions of years. When 3 Atlas was first detected, its unprecedented velocity could have inspired panic. But instead, astronomers around the world worked together. Within weeks, they had mapped its trajectory, determined its composition, and assured the world it posed no threat. That rapid, coordinated scientific response represents one of humanity's greatest achievements. It shows what we are capable of when we focus on understanding rather than fearing the unknown. The scientific harvest from this one object already exceeds what many astronomical discoveries yield in their entire lifetimes. Its carbon dioxide-rich composition has challenged existing models of comet formation, forcing scientists to rethink how volatile ratios vary among planetary systems. These findings are not just academic. They reshape our understanding of how worlds form, where water and other life-essential compounds come from, and which regions of the galaxy might harbor planets with conditions suitable for life. Perhaps equally important is the way the global scientific community responded. The Discovery Network that detected 3 Atlas, the Minor Planet Center that coordinated tracking, the Hubble and James Webb Space Telescopes that provided follow-up data, and ground-based observatories that contributed complementary measurements, all worked together seamlessly. The decision to make the data public reflects a philosophy that cosmic discoveries belong to all of humanity, not to any single institution or nation. Public engagement played a powerful role as well. Live tracking websites, press briefings, educational videos, and citizen science projects turned 3 Atlas into one of the most widely followed astronomical events of recent years. Amateur astronomers contributed valuable observations. Students analyzed the data. Thousands of volunteers helped monitor its brightness. This democratization of science is one of the most hopeful trends of the modern era. It reminds us that discovery is not just for specialists in observatories, but for everyone who looks up and wonders. Speculation, too, had its place. Some proposed exotic scenarios: alien probes, artificial acceleration, hidden messages. And while none of these ideas have been supported by the evidence, they encouraged researchers to define what would count as proof of artificiality, to design better observational tests, and to sharpen the boundary between science and speculation. This is how knowledge advances, by moving from mystery to understanding, from wild ideas to evidence-based conclusions. The entire investigation of 3 Atlas has been a case study in how science works at its best. Initial observations raised intriguing questions. Successive measurements refined the picture. Over time, evidence accumulated until scientists could say with confidence what this object is: an ancient, chemically unusual, but fundamentally natural comet, traveling through our solar system on its way back into interstellar space. This journey from uncertainty to comprehension is the true triumph, not the object itself, but the process by which we came to understand it. Looking ahead, the future is bright for the study of interstellar objects. The Vera Rubin Observatory will revolutionize this field, turning such discoveries from rare events into routine opportunities for research. With every new visitor, we will learn more about the distribution of materials in the galaxy, the processes that govern planetary formation, and the chemical conditions that may favor life. 3. Atlas connects us not just to other stars but to our own past, to the prehistory of the solar system, to the raw materials from which Earth was born, to the continuity of cosmic processes that stretch back billions of years. Its passage through our skies has expanded our knowledge, sharpened our tools, and deepened our sense of belonging in the universe. As we close this chapter, we are left with a sense of wonder and quiet optimism. The galaxy is vast, filled with mysteries we have not yet imagined. But if 3 Atlas has taught us anything, it is that we are capable of meeting those mysteries with curiosity, discipline, and courage. The universe still holds many secrets, but we are learning, piece by piece, to read its language. And that is reason enough to look forward to the next messenger from the stars, the worst-case scenario that initially drove our investigation. The fear of cosmic catastrophe or alien invasion has turned out to be unfounded. Instead, what we discovered was something subtler yet far more profound, a story of ancient chemistry, galactic evolution, and the extraordinary power of human curiosity. In replacing fear with understanding, 3i Atlas has given us perhaps the greatest gift any cosmic visitor could offer, a reminder that patient observation, collaboration, and reason can illuminate even the deepest mysteries of the universe. Good night, Cosmic Messenger. As 3i Atlas drifts outward from our sun, growing fainter with each passing night and melting back into the star-scattered darkness from which it came, we are left with images and data that will endure long, after the object itself has passed beyond the reach of even our most powerful telescopes. The Hubble Space Telescope has captured portraits that look like cosmic jewelry, a faint, star-like point surrounded by a gossamer shell of carbon dioxide, a glowing ornament suspended in the endless black of space. James Webb's infrared instruments have gone even further, reading the spectral fingerprints of that coma with breathtaking precision. Each line of its spectrum is a word in an ancient chemical story, a message from a place humanity has never seen. Trajectory plots show its path as if drawn by an invisible hand, sweeping smoothly through the solar system, past Mars, curving gracefully around the Sun at perihelion, and then arcing back outward toward the realm of the giant planets before heading once again for the void between stars. These are not chaotic, human-shaped paths full of politics, accidents, and unpredictability, but the serene geometry of celestial mechanics, as inevitable as sunrise and as dependable as the turning of the seasons. There is comfort in that reliability. In a world filled with human noise, crises, and uncertainty, 3i Atlas follows laws that have governed the cosmos since the dawn of time. Its departure is not determined by human choice, but by gravity, momentum, and the fundamental forces that shape the universe itself. In an age addicted to urgency and spectacle, there is something profoundly calming about this. The universe keeps to its schedule, no matter what we do. And so, the answer to our original question, what is the worst-case scenario, turns out to be almost disarmingly simple. Nothing at all. No catastrophe awaits. No invasion threatens. No cosmic event will disrupt Earth's orbit or climate. 3i Atlas will leave our solar system exactly as it arrived, silently, safely, and with perfect mathematical predictability. But calling this outcome mundane misses its real significance. The fact that we can predict the movements of an object that may have been traveling for billions of years, that formed around a star we have never seen, and that carries within it the chemical signatures of a place we have never visited. That is one of science's quiet triumphs. The same physical laws we discovered on Earth guide this wanderer's path through the galaxy. Its strange, carbon dioxide-rich composition has already forced astronomers to rethink what a typical comet looks like, expanding our understanding of what kinds of materials can form around distant suns. Its likely birthplace, in the galaxy's thick disk, offers a window into stellar neighborhoods far removed from our own, neighborhoods that existed in an era when the galaxy itself was younger, less chemically enriched, and very different from the one we inhabit today. Papers about 3I Atlas will be cited for decades. Its lessons will be folded into theories of planetary system formation, comet evolution, and galactic chemistry. Each strange fact about this object, its speed, its orbit, its chemistry, becomes part of a larger mosaic, helping us understand not just one interstellar visitor but the population of countless wanderers that must be drifting unseen between the stars. The wild speculations that filled the early days of this investigation, the theories about alien technology, ancient civilizations, or exotic propulsion were not wasted. They served their purpose by pushing us to ask bold questions and to stay open to every possibility. But the evidence has led us back to nature, to processes that are spectacular precisely because they are natural. The universe, as it turns out, doesn't need aliens to be mysterious. It already offers black holes, dark energy, quantum weirdness, and the accelerating expansion of space, a reality more wondrous and strange than fiction. If there is music to accompany our farewell to 3I Atlas, it should not be ominous or triumphant, but reflective, something like Holst's The Planets or Barber's Adagio for strings, music that holds both the mystery and the serenity of the cosmos. From the start, we have been careful to mark the line between what is known and what is imagined, letting the data guide us even as we speculated. That commitment to clarity is more than just intellectual honesty. It is a necessity in an age when rumors can outrun fact. The final lesson of 3I Atlas is not about impact hazards or threats from space, but about our own relationship with the unknown. Fear is natural when we encounter something beyond our understanding, but fear does not have to be our final response. Through careful observation, shared data, and international collaboration, we turned an object of cosmic anxiety into one of cosmic wonder. NASA's open archives, Hubble and Webb's images, and the work of ground-based surveys and professional astronomers turned this passing visitor into one of the best-studied interstellar objects in history. This is science at its best, not the work of one lone genius, but of a global network of researchers, observatories, and institutions, all collaborating to make sense of a traveler from another star. And as 3I Atlas fades from view, carried onward by momentum gathered over its billion-year pilgrimage, it leaves us with more than just data. It leaves us with hope. Hope that when the next visitor arrives, we will be ready to greet it with the same curiosity, the same instruments, the same shared commitment to understanding. Hope that as we continue to watch the skies, we will find more such messengers, each one carrying its own story, its own secrets, its own testimony to the history of the galaxy. The silence that follows its departure is not empty. It is full of expectation. Somewhere out there, another traveler is on its way, another fragment of a world we have never seen, carrying within it the clues to its origin, the echoes of its creation, and the next chapter in the story of our galaxy. And so we look up again, because there will always be more wonders, more questions, more cosmic messengers. 3I Atlas was only the beginning, a single note in a much larger symphony. Good night, Cosmic Messenger. Thank you for reminding us that the universe is stranger, richer, and far more beautiful than our fears could ever imagine. Safe travels as you vanish once more into the deep black sea of stars.